So, welcome to the 36th session of day 5, Wadla 3.0 on topic recent trends in deep learning. So, today we have with us Dr. Kaize Ding from North Western University. So, he is going to talk on data efficient graph learning. So, before his talk, I would like to introduce him. So, Dr. Cage is an assistant professor in the Department of Statistics and Data Science at Northwestern University. Cage's research interests generally lie in data mining, machine learning, and natural language processing, with a particular focus on graph mining, graph machine learning, data efficient learning, and reliable AI. His dedication and expertise have led to the publication of numerous high impact works in top tier conferences and prestigious journals. As a recognition of his contributions, Cage was selected as the recipient of several prestigious awards and honors, including ASU Graduate Outstanding Research Award, SDM Best Poster Award, Best Paper Award at the Trustworthy Learning on Graph Workshop, etc. So now I kindly request to Professor Kaize Ding to take over the session.
Yeah, thank you for the introduction. And it's my great pleasure to give a talk at this workshop. So in today's talk, I will gonna talk about my research on data efficient graph learning. All right, let's start. So as we know, um, right now, like the machine learning model and or AI model, they are super powerful, right? Especially the large language models. For those large neural networks, they usually require a lot of training data to stimulate the power of the training parameters. For example, for the GPT-4, it has over 1.8 trillion parameters, and at the same time, it was trained over trained on over 1 petabytes of text data. So as you can see, over the several years, the scale of the the language model has been dramatically increased, right? And so that's why like people say those like powerful AI models are actually data hungry beasts. But in many real world cases, we usually do not have so many computing resources to support us to build like a foundation model, especially for like domain specific applications. So that's why data labeling is still a bottleneck for us to build a machine learning model to solve the problem. And we know that the process of data labeling is usually quite labor intensive and resource expensive, right? One example is that like the ImageNet, it has over 14 million images from over 22,000 categories. Imagine that like if you want to label one image from those 22,000 categories, like it would be super hard for you, right? Even as like an expert. So that's why this data set took like over 25 years to annotate, and the efforts is still ongoing. So like in the real world scenario, when we do not have a lot of like label data, we only have like a small amount of label data. How can we like build machine learning models? And like we know for existing like or conventional machine learning models, for those deep neural networks based machine learning model, they usually fail when learning with only small amounts of labeled data. So this is because the samples we have, those samples cannot well characterize the whole data distribution, right? So, and in many cases, the data we have contain like outliers and also the missing values and even distribution shifts. So all of those issues will amplify the difficulty of learning a good machine learning model. For me, I'm actually more interested in the small data challenges in the graph learning context. This is because we know graph can be considered as a fundamental data structure for describing and modeling a spectrum of complex systems. For example, in the social media domain, we have the social networks, where the nodes represent the people or the edges represent the friendships. Similarly, in the biomedicine domain, we have the molecular graphs, and also like in the financial domain, we have like the financial transaction networks. All of those For all of those graph structure data, if we can leverage the knowledge of the graph structure, we can actually make better prediction for the target task. But one thing we should keep in mind is that like when we do the data labeling on the graph, because for graph data, it has like a multi-modalities. We usually need like more labeling cost to do the data labeling on the graph structure data. So it is even more challenging, right? So one example in the biomedicine domain is to do the molecular property prediction. So if we want label the data for training a machine learning model. So we need to go through a series of time-consuming and resource-costly web lab experiments to get the labels of the molecular properties. So that's why we usually only have like a small amount of labeled molecular graphs for like the majority of the molecular properties. So that's why we will have like the small data issue when we solve this molecular property prediction problem. And similarly, we will also have like many other small data graph learning challenges in the real world scenario. So what is the solution for solving this problem? So here, I want to call out that like actually there is like a missing piece in machine learning frontiers that can unleash the power of structured knowledge even with insufficient label data. And the thing is data efficient graph learning. So basically, we want to leverage like only limited label data, and by using the structured knowledge, we can like make better predictions on the machine learning task on the graph structure data. So for data efficient graph learning, our goal is to enable effective and reliable graph learning with low-cost human supervision signals. As you can see, my research in data efficient graph learning is motivated by some fundamental problems in this field. As you can see on the left hand, we have three fundamental problems. The first one is graph few-shot learning. So basically, for graph few-shot learning, we want to solve the problem that like transfer the auxiliary knowledge from some seen tasks to unseen tasks. And for those unseen tasks, we usually only have like a few labeled examples. So we want to leverage the auxiliary labels from the seen tasks and transfer the knowledge to the unseen task. So here we want to like improve the transferability of graph machine learning models to solve this problem. The second problem is about like a graph weakly supervised learning. So basically, in real world scenarios, we instead of have the like a gold label data, we only have like a weak supervision signals. So the weak supervision signals could be like limited or noisy or even coarse grained. So we want to leverage such like weak supervision signals and mitigate the negative impacts from those weak supervision signals and improve the reliability of graph machine learning models. And lastly, we have the graph self-supervised learning problem. Basically, we don't have any labels for the downstream tasks. We want to leverage some like synthetic labels. We create synthetic labels to pre-train the model. So we learn generalizable representations from the graph structure data, and we can leverage such generalizable representations and quickly use them to quickly generalize to different downstream tasks. This is the fundamental problems in data efficient graph learning. And at the same time, I'm interested in applying like data efficient graph learning algorithm to the real world applications in different domains. So basically, we want to leverage the domain knowledge from those different domains and incorporate those domain knowledge into the design of data efficient graph learning algorithms and help us to solve those applications. For example, in the cybersecurity domain, we can like do anomaly detection or disinformation detection, and we usually don't have a lot of label data. We just want to like leverage limited label data and leverage the structured knowledge to solve the problem, right? And similarly, in the information retrieval domain, we can do like a graph-based recommendation, or like in the natural language processing domain, we can do like a graph-based natural language processing. We can do a lot of NLP tasks on the text attributed graphs. Yeah. So in today's talk, I will not like go through all of those subfields in data efficient graph learning. So I will mainly focus on the graph weakly supervised learning and graph self-supervised learning. But I will use some like representative work in those different fields to talk about those two research fields. Okay. Let's move to the graph weakly supervised learning. So for graph weakly supervised learning, as I mentioned, there are different types of weak supervision signals, right? So one type of weak supervision signal is incomplete supervision, meaning that we only have very limited label data for the target task. And we also have the inaccurate supervision signals. This is about the scenario we only have some like noise labels, right? And we want to denoise from those noise labels on a graph. And lastly, we have some like indirect supervision signals. So those indirect supervision signals could be from like a co-screen labels or from another auxiliary task that is different from the target task. So we want to leverage such knowledge and help us to solve the target task on a graph. So in today's talk, I'm going to focus on the incomplete supervision and talking about my one of my work on graph few-shot semi-supervised learning. Okay. For the problem of graph few-shot semi-supervised learning, the setting is pretty simple. We on a graph we have like different node classes, and for each class we only have very limited label nodes, and we want to leverage those limited label goal label nodes, and as well as the large amounts of unlabeled nodes to help us build like a very powerful graph machine learning model. To build this kind of data efficient graph neural networks, one potential solution is to enlarge the receptive fields of graph neural networks. So this way we can better propagate the feature patterns of the label nodes to the unlabeled nodes throughout the graph, right? As you can see, if we increase the depth of the GN layer from 1 to 3, we will have like a larger receptive field on this toy graph, right? As you can see, for the node of interest, it can propagate the information from the information to its 3-hop neighbors. So basically, the 3-hop neighbors will reach almost every corner of this graph. So that's why the information can be like a better propagated along the graph. And based on this intuition, if you like build like a very deep graph neural network, so the model should be like more data efficient or label efficient, right? But can we simply build like a many layer GNN to solve this problem, to solve the few-shot semi-supervised learning problem? According to our empirical results, unfortunately, no. As you can see here, we show the model performance of the graph convolution networks with different layers on the core dataset. If we like with increasing the layers of GCN, at the beginning we will see the performance gain, right? But by considering like a high order information, but later on with increasing the depth of the layers, the performance gradually decrease, and it will like finally decrease to like a linear model. Um, so the why we will have this problem? So why do we like why having larger receptor field, we still cannot like get a very good performance on this kind of few shot semi-supervised learning problem. Uh, so before we go deep into the design of the model, so we want to know the reasons that cause the problem, cause the performance decrease, right? So there are like two main problems cause the performance decrease. The first problem is the over smoothing issue. As we know, even though like we increase the depth of the gene layer, we'll have like more, we'll have like a larger receptor field. But for different nodes, they're like uh, uh, for different nodes, their shared neighbors will also have like a huge overlap. As you can see in this example, if we consider the 3-hop neighbors of 2 different nodes, they will have a lot of shared neighbors, right? So when we like compute, when we like visualize the computation graph for those different nodes, it we cannot like will distinguish those 2 different nodes from the computation graph, and we cannot learn distinguishable representations for them because they all aggregate the information from those like 3-hop neighbors, and there are like a huge overlap between them. So finally, we have the over smoothing issue by simply increasing the depth of the gene layers, and another important problem causes the like performance decrease is overfitting, because if we want to build like a very deep GN model, we have like a lot of training parameters, but because we only have very limited training data, the model will easily overfit to the training data, right? So like the learning model cannot real generalize to the testing data, especially if there is like a distribution shift between the training data and the testing data. So also like we need to keep in mind that like because we are using graph neural networks, it has the message passing message passing mechanism. The prediction errors will also be propagated along the graph structure when we do the message passing, and also if we have like a very deep GN model, the gradient vanishing issue will also make the training even harder. So that's why like we'll have like a severe overfitting issue, like when we simply build like very deep GN model and cannot get a very good performance on like on those kind of low resource setting. So to solve this problem, we came up with an idea based on a very classical graph learning algorithm, which is called like label propagation. So label propagation is like a very classical algorithm, and with like a very simple idea. It just propagates the labels from the label nodes to the unlabeled nodes. But the good thing about this algorithm is that like it allows large propagation steps without over smoothing inherently. So as you can see on the left hand, like this is the objective of the label propagation algorithm. So we want to make sure 2 constraints. The first one is the smooth constraint. We want to make sure that the propagate labels are smoothed along the graph structure. On the right hand, we have the fitting constraint. We want to make sure the propagated label matrix is close to the original label matrix. If we use personalized PageRank to approximate the closed form solution for the objective, we will get like an iterative propagation function on the right hand. As you can see, for each propagation step, we will still keep part of the information from the original label matrix Y0, right? Um, which is controlled by the alpha here. So if we set like an appropriate teleport probability, which is the alpha here, the label propagation algorithm can enable large propagation steps without losing focus on the local neighborhoods. We will still keep the information from the original label matrix. So that's why we will not have the over-smoothing issue. And another benefit of using label propagation is that like we can like propagate the labels to the unlabeled nodes to get the pseudo labels, and we can incorporate such pseudo labels into the training process and help us to mitigate the overfitting issue. So based on the idea of label propagation, we first derive a base model. It is a decoupled architecture that decouples the propagation and transformation operations in each gene layers. So we know that like for gene layers, there are two essential operations, which is the feature propagation and the feature transformation, right? So here we basically, we can simply decouple those two operations to two different steps. As you can see, given the input graph, we first use label propagation to propagate the labels from the original goal label nodes to the unlabeled nodes. We will have the augmented graph with a lot of pseudo label nodes, right? And based on after that, like based on the augmented graph, we can do the feature label transformation and transform the features of the of all of those nodes to their like corresponding labels, and use the based on the cross entropy loss, we can learn the model and make prediction on the unlabeled nodes, right? And in our work, we actually prove that the label propagation plus feature transformation is a kind of a special case of graph network. So here we call it as like a decoupled graph network. But even though like a feature propagation plus label propagation plus feature transformation works fairly well, but there is like a huge limitation of using this idea. It's mainly because of the blindness of label propagation. We know that label propagation usually follows the homomorphy principle, and it uses a fixed label propagation strategy. That means it cannot always generate meaningful pseudo labels for the target task when the graph has like different properties or like different label ratios. This is mainly because the phase of the module of label propagation and feature transformation, they have two disjoint objectives, and the label propagation cannot be informed by the process of feature transformation, right? So so here, the next question we want to ask is like how to adaptively adjust the label propagation strategy. So this way we can adaptively generate the pseudo labels and help us to get a better performance on the few shot semi-supervised learning setting. Okay, so here to solve this problem, we propose like a meta-learning algorithm that can connect those two different two disjoint learning objectives. So here we first have the meta-learning objective. So the objective is like the pseudo labels generated by the adaptive label propagator or the meta-learner should maximize the performance of the feature label transformer, which is the target model on the small set of labeled training nodes. So as you can see, here we still have two like modules, the adaptive label propagator and the feature label transformer. But the different thing is we first use the adaptive label propagator to propagate the labels and get the pseudo labels. And based on this augmented graph, we directly transform the features from the pseudo labels, not all the labels or all the labels from all the nodes. We just use the pseudo labels and transform the features to the labels and learn this feature label transformer. And after that, we evaluate the performance of the feature label transformer on the originally goal label nodes. So this way we can get a loss and use this loss to guide the learning process of the adaptive label propagator. So this way we can like the adaptive label propagator will be informed by the performance from the feature label transformer, and we can like adaptively adjust the label propagation strategy. Okay, so for the meta propagation networks, which is MetaPN in this work, there are two main components, as I mentioned, right? So the first one is the adaptive label propagator. This is the meta learner in our model, and we just use like attention words to control the contribution of different propagation steps. So basically, it is attention module, and we use this attention mechanism to control the contribution of different propagation steps. And another component is a feature label transformer. So the feature label transformer is the target model, and we transform the node features to the propagated pseudo labels via through like a multi-layer perceptron. So as you can see, both of those two components are like non-graph networks, right? So they just based on the multi-layer perceptron. So the building blocks of this model is very simple, and we can for the target model we just use cross entropy to learn the model based on the predicted label and the propagated label, and so this model will be like very simple and efficient. The main challenge of learning this model is about the model optimization problem, optimization part. So we know that the target model parameters are depend on the parameters from the meta learner, right? So this is why the learning to propagate problem is like a bilevel optimization problem. So to solve this bilevel optimization problem, we use like a we alternatively update those two modules. So on the lower level, we use like a one step gradient to approximate the optimization step. So basically, we update the target model using the pseudo labels generated by the adaptive label propagator, and compute the gradient. And on the upper level, so we update the meta learner, which is the adaptive label propagator, based on the performance or the loss of the target model on the originally labeled training set. So by iteratively update those two models, we can finally learn a better adaptive label propagator as well as the feature label transformer. So we can learn a very powerful and label efficient graph learning model for the graph few shot semi-supervised learning problem. Okay, so for our model meta propagation networks, we evaluate its performance on different few shot semi-supervised learning scenarios, and we compared its performance with different lines, different categories of baselines. So here, as you can see, we compared it with like a conventional graph networks or semi-supervised learning algorithm on graph, and we also incorporate label efficient graph networks or like deep graph networks in the experiments. And finally, we incorporate those like graph self-training methods that can incorporate the pseudo label or like the pseudo nodes into the learning process. But from the experiments, we can see that like a MetaPN can consistently outperform all of those baselines. on this on the graph few-shot semi-supervised learning setting. This is mainly because the MetaPN can inherit the advantages of both the graph self-training methods and deep graph networks. So we know that like by decoupling the transformation and propagation steps of graph networks, we will not have the over smoothing issue, and we will have like a large receptive field, right? And also because we leverage those pseudo labels, we do the label propagation, we can also like leverage the advantage from the graph self-training methods. So that's why our model can achieve like better performance. And on the right hand, we show some analysis regarding the over smoothing issue. As you can see, MetaPN compared to two like important baseline GCN and the base model label propagation plus filter transformation, it achieves like better performance. The GCN model will like have the over smoothing issue and get the performance decrease when we increase the layer depths. But and for the base model label propagation plus feature transformation, it still cannot get the best performance because of the blindness of label propagation strategy. So the MetaPN can adaptively adjust the label propagation strategy and get a better performance compared to them. Okay, and beside the evaluation on the graph few-shot semi-supervised learning setting, we also evaluate MetaPN on the standard semi-supervised node classification setting, and as well as on the large scale dataset. As you can see, even though MetaPN is not specifically designed for the standard semi-supervised node classification setting, so in this setting, each node have like a relatively abundant label nodes. Usually we use like 20 label nodes per class. But our model MetaPN can still like achieve like very competitive performance when we compare to different baselines here. And also on the large scale data set, because MetaPN can adaptively adjust its label propagation strategy, so the model can get like a very stable performance on different learning settings. Okay. All right, so for this work in graph weekly supervised learning, do you have like any questions? Or yeah, if you have any questions, feel free to ask.
Professor, there is one question in the chat box, so I am just reading it. So, what is a gold labeled and pseudo labeled nodes?
Oh, okay. So for the gold label nodes, meaning that those labels are ground truth labels. There are no noise like in the gold label nodes. So for the pseudo label nodes, we know that like those pseudo label nodes are generated by the model you learned. So you like first learn a model and you use the learned model to predict the pseudo labels on the unlabeled nodes. So those are the pseudo labels nodes. The pseudo label nodes usually have some like a label noises, some like a mislabeled nodes. So that's why we need to consider this issue when we try to incorporate the pseudo label nodes. Okay, all right. So if there's no other question, I will continue on the like graph self-supervised learning problem. Okay, for graph self-supervised learning, the goal is basically to learn generalizable representation without using any human entity labels. So in general, there are two popular paradigms for graph self-supervised learning. One line of research is called graph generative modeling. Basically, we try to learn generalizable representation by reconstructing the node features or the graph structure based on the representation we learned from the graph. And another more popular line of research is called like graph contrastive learning. Basically, for graph contrastive learning, we first use data augmentation to create different views from the unlabeled graph. And based on the graph, we want to, based on different views of the original graph, we want to maximize the agreement between the representations learned from different augmented views of the same instance. So as you can see on this example, we have like two nodes, the red node and the yellow node, and we consider it's like two hot neighbors. So we do the like subgraph sampling for those two different nodes. If we consider the first subgraph as the anchor, we will have like one positive example, right? And for the yellow one, we will also have like two subgraph, and we will consider those two subgraph as the negative example for the anchor graph, right? So during the contrastive learning process, we want to maximize the similarity between the positive pairs and um, try to like push away the representations for the negative pairs. So this way we can learn distinguishable representations for each node. So when we try to develop like a graph contrastive learning algorithm, so there are three focal points we need to consider when we try to design an algorithm. So the first thing is about like a graph data augmentation. So we know that for data augmentation, we need to create the different views of the of each instance. For example, the node or an edge, right? So existing methods, they usually adopt like an arbitrary graph data augmentation. For example, the edge dropping and feature masking, those kind of operations uh, to get the augmented views. But those data augmentations, they may like disturb the original semantics of the of different nodes, right? And for the encoding backbone, the second thing we need to consider is the encoding backbone. And the encoding backbone usually try to like encode the augmented views and learn the representations for those different augmented views. And we know that the existing models, they usually just consider the shallow graph networks, for example, the two-layer GCN to encode the augmented views. But we want to like capture like high order information. We want to like make it more expressive, basically. The final thing we need to consider is about the contrastive loss. And we want to maximize the agreement between the representations learned from different augmented views. So existing methods, the limitation is that like they only consider the instance level contrastive learning. They want to like maximize the instance level like a discrimination. But in some cases, we want to like consider like a consider like a semantic meanings of different instances. So instance level contrastive learning is not enough in those cases. So if we want to address the limitation of existing graph contrastive learning, we need to build like a new algorithm. And we know that like those existing methods, they cannot solve like some like very challenging problem in the real world setting. So this problem, so here I give an example of, about this problem. So we know that like in real world scenarios or real world graphs, the nodes sharing similar properties, they may not always be closely connected on a graph. So this the example here is about the twin strangers in the real world friendship graph or friendship network, right? Those two people are pretty similar to each other. They even look like very similar to each other. They have like a very similar profile, but they could be totally unrelated on the graph. But existing graph networks or like unsupervised graph contrastive learning methods, they cannot attain such global awareness. They only consider the local neighborhoods, so they cannot make sure those two different nodes will have like similar representations, um, like in the latent space. So that's why we want to learn kind of a global graph contrastive learning methods that can attain such global awareness. So for the current graph contrastive learning algorithm, the main reason that cause the shallow property is are from like two different perspectives. The first thing is from the structural perspective. This is mainly because the shallow graph networks, they cannot capture the long range node interactions in nature. And we actually already talked about this issue in our last work, right? So even though we increase we increase the depth of the gene layer, we will have the oversmoothing issue. So we need to solve this problem. And more importantly, in the semantic perspective, because as mentioned, existing graph contrastive learning methods, they mainly focus on the instance-wise discrimination. They cannot like maintain a semantic structure in the latent space from a global view. So as you can see in this example, here we show like 3 different nodes, and in each circle, we have like different possible augmentations of this node, augmentation representations of the node. And so you can see if we consider the node 1 as the anchor point, we will have like 2 negative example and 1 positive example in this here, right? So if we just apply the instance level contrastive learning, we will push away the representations of those like negative pairs. But we know that the node 1 and node 3 could share like similar semantics. They will have like a similar label in fact, but those negative pairs that share like similar semantics will be undesirably pushed away in the latent representation space. So we cannot address this problem like by just using current graph contrastive learning algorithm. So we want to build a kind of a global graph contrastive learning algorithm. So based on those intuitions, we try to develop like a new algorithm that can elicit the structural and semantic global knowledge. And the model we build is called S-cube-CO because it is a very simple simple neural network that can capture the structural and semantic knowledge from 2 different contrastive learning algorithms. As you can see, for the graph data augmentation part, we first use multi-scale feature propagation to generate different augmented views for the input graph. And for the encoding backbone, we just use like a simple neural network. In this case, we just use a 1-layer neural network. So we don't need, we no longer rely on the graph networks. And for the contrastive learning loss here, we developed like 2 new algorithm, the structural contrastive learning algorithm and the semantic contrastive learning algorithm. So and this way we can capture or like elicit the structure and semantic global knowledge in the learning process. Okay, so first we're gonna talk about the structural contrastive learning algorithm. So for this algorithm, basically we want to exploit both the local and global structure knowledge for learning expressive node representations. As you can see, given the input graph for each like anchor point, we do like multi-hop feature propagation. So for the same node, we consider like the representation learned from different hop feature propagation as the positive samples, and we consider the representations learned from the other nodes, the rest of the nodes, like as the negative samples. So this way, we can consider the global structure knowledge and build this kind of a structural contrastive learning to exploit both the local and global structure knowledge. So this way, we can maximize the agreement between the representations of each node learned from its local view and different higher order views, right? And another important algorithm is the semantic contrastive learning algorithm. For semantic contrastive learning algorithm, basically we want to capture the global semantic knowledge by enforcing the intra-cluster compactness and the inter-cluster separability. So as you can see, so here we have like a different clusters. We want to develop a cluster prototype inference algorithm to first infer the clusters and the cluster prototypes. And we want to perform the contrastive learning between each node and its corresponding cluster prototypes. So this way, we will make sure for each cluster, we will have like very compact representations for different nodes that share like similar semantics. And for different clusters, that those can be like very, very well separated. And for the cluster prototype inference algorithm, basically we use like Bayesian non-parametric clustering. And this algorithm is pretty simple and very similar to k-means. But the different thing is for each step, we first, for each node, we first reassign the node to the cluster corresponding is to its closest prototype. But we should note that like if the distance to the closest prototype is greater than a threshold, we will initialize a new cluster. So this way, we can automatically infer the number of clusters and the cluster assignments. And for the cluster, for each cluster, we will update the cluster mean based on the cluster assignments. So we can like iteratively repeat this process and get the cluster assignment in the latent representation space. Okay, to optimize the algorithms we built, so here we show the optimization of the S-cube-CO model. So basically, given the observed data, which is the graph, the attributed graph we have, we also like have the encoder parameters, which are the theta here, and we also have the latent variable, the prototype assignment Z, and the prototype representation C here. So our objective is to maximize the log likelihood of the observed data through the online EM algorithm. So for the each step, we first fix the network parameters, and we estimate the prototype assignment Z and the prototypes C with our proposed cluster prototype inference algorithm. And for the M step, we try to maximize the expectation of the log likelihood of the observed data by directly optimizing the contrastive loss function with regard to the network parameter theta here. But one thing we need to like note that like instead of just optimizing the semantic loss here, because we want to exploit both the structure and semantic global global knowledge, we optimize the structure loss and the semantic loss together in the app step here, as we can show in the learning objective here. And to evaluate the performance of the model, of our model S-cube-CO, we first learn the representations of different nodes through our model and evaluate and leverage the learned representations and evaluate its performance on different downstream tasks. So one classical or like a benchmarking task is about like a few shot node classification. So here, as you can see, we compared with different self-supervised learning and fine-tuning algorithms, our model SCOOP-CO can achieve better performance. This is because the nodal representation learned from our model can encode better global knowledge, and like in some cases, even comparing with compared to like some semi-supervised learning model, our model can achieve like a very close and even better performance than them. And also, we show the model performance of different models under the low data scenarios. As you can see, our model can achieve very stable performance under the extreme low data scenarios, which means the model, the quality of the learned node representations are better than the baselines. Another task we evaluate is about like node clustering. So this task is very simple. We just try to cluster, is just to cluster the representation learned from different nodes. And as you can see, our model also like achieve better performance than the model compared to the best performing baseline, the sugar here. We visualize the representation learned from those two models. As you can see, our model SCOOP-CO on the bottom it can like achieve better intra-cluster compactness and inter-cluster separability. This is mainly because our like semantic contrast learning algorithm, so it can like maintain this kind of semantic structure in the latent representation space. Okay, so because our model is very simple, right, for the encoding backbone, only leverages like a simple neural network, like 1 layer or 2 layer neural network. So we no longer need like a very deep graph networks to encode the like high order information. So that's why like SCOOP-CO has very huge advantage in saving the computation memory, and we for the data augmentation part, we do the feature propagation in the pre-processing step, and we no longer need to do the like a propagation during the learning process. So as you can see, SCOOP-CO is very simple. When we test the memory consumption on different like in terms of like different hop of neighbors or like different hops of message passing, our model is like the most efficient one. Even we have like a 10 hop, we consider 10 hop neighbors because those baselines they need to build like a 10 layer GNN to achieve the same expressiveness of the model. Their model parameters or like memory consumption will be increased a lot, but our model will not be increased in this case. So that's why SCOOP-CO is very efficient in terms of the like model parameters. Okay, so so far I have talked about like two like important research like in data efficient graph learning, the graph weakly supervised learning and graph self-supervised learning. So at the end, I want to mention that like data efficient graph learning is still actually in its infancy. So we need to build like more theoretical understanding or like domain specific applications for this topic. And here I listed some like useful learning resources for data efficient graph learning. So if you are interested in like feel free to like go through them. And like if you have any questions, you can also like send an email to me. So here we have the surveys about like data efficient graph learning. And we also like have some like tutorials about data efficient graph learning in like some like recent conferences. And here we also like recently build like data efficient or label efficient graph anomaly detection library, which is published in like last year in Europe. And if, you can like try it out, like if you are interested. All right. This is pretty much of my today's talk. So any questions?
So thank you very much, Professor, for your wonderful talk. So, really, your talk was very informative. So I would request the participant to ask the questions if they have.
Hello, Professor. Thank you for
Hi.
wonderful talk. It is really useful. I'm
Thank
curious
you.
to know,
Mm-hmm.
you're welcome. I'm curious to know how you managed with the meta-learning algorithm, because of the two loops, outer and inner loop, usually it would blow up the complexity, right? So how compute intensive is it? Can you just provide some clarification? The
Yeah,
first
like
part.
yeah. I know for the bilevel optimization problem. Yeah, I know it's like sometimes it's very complex to solve. So here we just adopt like a simple solution. We in the inner loop, like we use like one step gradient to approximate the solution for the inner loop optimization. And I believe there are a lot of following work about like improving the efficiency when handling the bilevel optimization problem. And we can definitely like explore those algorithms and like incorporate them like into like our framework and improve the efficiency or stability of the model.
Okay, so we have to look for the optimization in the inner loop. Thank you. And with reference to the second work, like you are using clustering and your results are really great, like in the low data scenarios. I am really curious how intuitively in a low data regime, with clustering, you can achieve those results. Can you give some intuitive explanation for that wonderful result?
So the intuition why we can get like a better performance like in the low data scenario.
Yeah.
Okay. Yeah. So because like this is because our model can like learn like a more expressive representation for the nodes. Like as I mentioned, like because we do like a multi scale like feature propagation, right? Like we can capture the high order information for each node. Basically, the feature representation will be like more expressive, and also like we learn the semantic structure, we maintain the semantic structure by using our semantic contrast learning algorithm. So basically the representations we learn are more expressive than other algorithms. So that's why we will only have like very limited labeled data or labeled nodes when we do the node classification downstream task. We can still like get a very good performance under the low data scenario.
Oh, okay. Thank you.
Yeah.
So
thank you.
I have one question, Professor. So would it be possible to generate the pseudo label in zero sort learning scenario?
Can you repeat the question again? Like, can we generate the pseudo labels in what scenario?
Zero sort learning. Zero sort. Few sort means few sort you have been generating. So I'm just asking. So would it be possible to generate the pseudo label in few sort learning? Sorry, zero sort learning.
Oh, zero sort learning, right?
Yes.
Yeah, that is a good question. I think. I think it could be possible. So because for the zero shot learning, if you have the semantic description for different labels, probably, yeah, you can still because like, yeah, if you design the, I mean, for the inner loop, like if you design some like evaluation metrics to measure the performance of the zero-shot learning task. And you can still like use this kind of a bi-level optimization or meta-learning algorithm. But right now, I don't have like a clear solution for that. Like I think it could be like promising to explore this for the zero-shot setting. Yeah, this is a good question, I think.
So thank you very much, Professor.
Yeah.
Despite your busy schedules, you are attending the Neuro IPS conference, and still you agreed and you have given this wonderful talk. So really, I appreciate you, Professor. And in future also, we would like to invite you in such kind of workshops. So thank you very much.
Thank you. Yeah, nice to talking to you guys. Yeah.
Thank you.
See you.
Thank you.
Yeah, thank you. Bye.
Bye.